All right, our next speaker. Our next speaker is Dr. Ethan Siegel, who is an author and columnist. You may have read some of his popular science communication on forums, for example, is where I've read most of his work. But he also writes books. He is an author. And he has this book for sale here right now, and you can get him to sign it. It's called Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe. Speak to Ethan afterwards if you would like a copy. Please join me in welcoming Dr. Ethan Siegel.
All right, everybody in the back, can you see my space kilt? Thank you. All right, so the question portion of this, the quiz portion is over. I am very much in the, I am just going to give you all the answers. So many of you have learned a lot of things about what has happened in the universe so far. We've had 13.8 billion years of it being pretty good. And I'm going to spend the next 15 to 20 minutes giving you the entire rest of the story. So if you would like to know where everything is headed, let's see if we can cover it all. And here we go. So, wait, this is going to work, right? Okay, so here's what we're going to talk about. I'm going to go real quick and give you what the universe actually is. If you do not know what the universe is, that's okay. We're going to cover that first. Then I'm going to talk to you about what the possible fates are, what we observe, what we think is going to happen, what the fate is of planets, stars, and galaxies, and finally, what that means for the entire universe. If that's all a lot, you don't have to remember it. I'm just going to give you the answers. So, what is the universe? Sarah showed you a great picture of a telescope called the Sloan Digital Sky Survey. This is a result from the Sloan Digital Sky Survey. And if you don't know what it is, it's because you've probably never seen anything like this before. What this is you know that the Milky Way shines through the galaxy. And if you look at the North Pole of the Milky Way, you don't get any of the Milky Way stars in the way. So what the Sloan Digital Sky Survey did was it looked in that region of space, and everywhere it found a galaxy, it said, okay, I'm going to take some data there. That's a point. This is an image of 400,000 points from looking at the North Pole of the galaxy. Every point in this image is a galaxy. And what you see is that some points are big clusters of galaxies. Some points are big voids where there are very few galaxies. And you get this sort of weird web-like structure. If you take a look at our theory and what we predict, this is the cosmic theory of what we should form. So the answer is, we should get a web-like structure. We see a web-like structure. That's what the universe looks like today. Where you have these big nodes, you should have big collections of mass. That's where gravity wins the most. You get thousands of Milky Way-like galaxies all together. Along these little filaments in the sparse regions, you get little beads of galaxies, little tiny groups and clusters like us, where we've got us and Andromeda and about 50 or 60 like little monsters, and that's it. Right? And then you have these big voids. These are the big cosmic losers. They give up all their matter to everyone else. You don't form stars or galaxy theirs. And this is weird, because most places in the universe are like that. Most places in the universe are these big empty places. You are very, very fortunate to be in one of these little matter clumps where you're actually on a planet. If you would say, what's the average density of the universe? If you took all the matter in the universe and you smeared it out, and you say, what's the density of that versus what's my density now? It's a 1 with 30 zeros after it is how much more dense we are here than the average. So that's pretty good. All right. What else is out there? So if we look at just a narrow region of space, right, you would say, oh, like there's galaxies here. And you would look at this image and you'd say, yeah, there's like big galaxies, and then there's like small galaxies, and that's what it is. And That's right, that's totally wrong. What am I doing here? No, these galaxies are pretty much the same size. The ones that look smaller are just further away. So that's why what Sarah showed you, if you looked farther and farther back, right, at that big Hubble Deep Field image where she showed you a couple of stars, that's just a tiny fraction of this image, of something like this, where you look super deep and you can see the farther you look, the fainter you look, the more distant an object you can see. So it's easy to see the close ones because the light doesn't spread out as much, but the farther away you go, the harder it is to see. But everywhere we look, we see stuff. We see galaxies. This is something we see on a much smaller scale. We see individual stars with solar systems around them. This is not our solar system. This is the TRAPPIST-1 solar system, about 40 light years away. So this is a new discovery. Since the 1990s, we've begun finding planets around other stars. And what we've learned, surprise, surprise, is that most stars have planets. And most stars have planets that are different from the ones we have in the solar system. Most stars will have either planets that are like gas giants that are close to their star, or they will have planets that are bigger than Earth but smaller than the gas giants we have here. Our solar system is just one possible outcome of a huge diversity of stuff. So our universe is full of stars and galaxies with these heavy element planets and chances for life. That's the big lucky thing in our universe, is that we have all of these complex atoms and molecules that come together and they make interesting things, right? That's what we are, is we're an interesting thing. This is great because the universe wasn't born with us. The universe wasn't even born with the right ingredients to make us. But things unfolded in such a way that here we are. And there is a whole great cosmic story about this, about how the Big Bang happened and everything expanded and cooled. And you formed neutral atoms when it cooled enough. And these atoms came together under the influence of gravity to form the first stars. And the stars lived and died and exploded and put these heavy elements back out into space that formed the next generations of stars. And galaxies merged together. And after 13.8 billion years, here we are. That's background. Right? We make stars, we know that. Stars live and die. The universe has expanded now. Anywhere we look, 46 billion light years in any direction. Which is interesting because I told you the universe is 13.8 billion years old. You guys know nothing can move faster than the speed of light. And I tell you now that the universe is 46 billion light years in any direction. Does my math add up? Okay, this is the #1 question I get writing about cosmology on the internet. But the way it's normally asked to me is, you can't even do math. How does that happen? The answer is because space itself is not a static thing. If all we had was like, oh, we got space here and there it is, and now we're going to have a big bang, and things are going to expand out at the speed of light, they'd be 13.8 billion light years away. But space is something that can expand. Space itself can expand. That's an important thing to realize. So it's not like I just threw something away from me. It's like I have a moving walkway, and I roll something away on the moving walkway, and the walkway moves, and the thing moves, and that's how it can get even farther away. So the universe doesn't really care about what's on your moving walkway. The universe cares about how fast is space itself expanding and what's all the stuff in the universe. And that's what determines how fast it expands. We want to know what the future holds, right? Or apparently we want to know what could the future hold. So what happens when we look back? That actually is where we find the answer. You don't think about this in like the Dr. Phil way of the best predictor of future behavior is past behavior. But instead, that was terrible, I'm sorry. But But the way you look at this is if you look back at the universe, if you look at what it was doing in the past, you can figure out how fast is it expanding now? How fast was it expanding then? And what are all the different things it was made of? So if we say, oh, like I can look at the galaxies that collided, and I can look at the distant nebulae that formed stars and what happened out there in the past, and I can look at the stars that lived and died and recycled their heavy elements into the universe, that's all the past. But the farther back I look at these things, the farther back I look at all the different ways I can measure what was the universe like in the past, that helps tell me what it's like in the future. So imagine now, we've gone all the way back to the Big Bang, right? So everything is hot, dense, and expanding super fast. What's going to happen? You're going to have two things fighting each other. It's like a race. On one hand, you have this initial expansion, pushing everything out, trying to drive space apart. That's the expanding universe. But on the other hand, we know that the universe is full of stuff. And it didn't just come out of nowhere. That stuff's been around since the universe was born. So what happens? You have these two forces fighting each other. You have the initial expansion and you have gravity trying to pull everything back together. Who's going to win? That's what you would say. Oh, let's examine all the possibilities. That's how we're going to do it. That's how we know who's going to win. So maybe, like Goldilocks, the porridge is too hot, right? Maybe the universe has too much mass in it. So what happens if gravity wins? You can imagine it, right? Like the space is expanding, it's getting farther and farther apart, but gravity is like, ah! It's going to pull everything back together. It's going to try and drive everything in. So you're going to hit some maximum size, and gravity's still going to be pulling, and things are going to turn around, and the universe is going to recollapse, and you had a big bang, and before you know it, after a certain amount of time, you end in a big crunch. So that's one fate. The other is, what if we're down here, right? What if it's the other way? What if the porridge is too cold? What if the expansion wins and there's not enough gravity? Well, then you'll expand and gravity will slow you down, but it won't slow you down enough and you'll just expand forever and ever and ever. And the last one is that other Goldilocks possibility. Maybe it's just right. Maybe the universe is going to expand and try and reach some maximum size, and gravity's going to try and turn it around. It's going to be perfectly balanced. Where if you had one more proton, you'd recollapse. But it doesn't. Instead, the expansion rate just asymptotes to zero. Everyone knows what an asymptote is if you have student loans. Okay. So these are your three possibilities here. It depends on who wins the cosmic race. Does expansion win, or does gravitation win? If expansion wins, then you're this top line, right? You expand, 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 and gravity tries to slow you down, but it fails, and here you go, you're just going to expand forever and ever and ever. Or, if gravity wins, you recollapse, and boom, your universe comes to an end over here. Or you can be in the middle and just be like on that Goldilocks case forever and ever and ever. So that's what we thought for years and years and decades, the fate of the universe is going to be one of these three. And the whole field of cosmology, which is my field, was the quest to measure what's it going to be. I said I'd just give you the answer. They're all wrong. Everything is not right here. None of these is the answer. So what is the answer? I want you to think about something. What is, right, I told you the expansion rate is determined by what's in your universe. So imagine your universe is filled with matter and it's expanding. Well, matter is just stuff, right? And so as your universe expands, you got the same amount of stuff, but it's getting less and less dense, right? So the more your universe expands, the volume goes up, the mass stays the same, so the density goes down. And that's it. That's how your universe would work if all you had was matter in it. And so you can see the expansion rate drops over time. What about if you got radiation? Radiation's a little bit like matter because it's just stuff, it's just photons, it's just these particles, except they also have wavelengths. The wavelength of radiation is what determines how energetic it is. So if I take this space, and I have these tiny, tiny wavelengths because everything's close together, and I stretch my space, what happens? These wavelengths stretch too. When you make a wavelength longer, it gets less energetic. So if I take a wavelength like this and a one that's 10 times as long, the one that's 10 times as long has 10 times less energy than the one that was shorter. The universe has expanded by factors of trillions and trillions since the Big Bang. So it's lost a lot of energy. And you can kind of see that in this line that doesn't show up, that, right, this falls off faster. But what if there was some extra type of energy? What if there was this type of energy that just was inherent to space itself? What if I just said, what about the energy of space itself? It doesn't drop, right? Because if I have this universe and then I have this universe, there's just more space now. So if there's any type of energy that's inherent to the fabric of space, then as space grows, this energy is just growing. In this case, the expansion rate remains constant. It doesn't drop. So as your universe grows, it's like you're just making more and more of this new type of energy if there's any non-zero energy to space itself. So this is what Sarah was telling you they discovered in 1998 looking at supernovae, right? That you look at these faint ones, and then you look at these more distant ones, and you said, oh yeah, right, if the universe were like down here, this would be the closed case where it recollapses, the big crunch case. This middle line here would be the intermediate case where it's that Goldilocks porridge is just right? And this would be this third line up here, that's the open case. That's the case where the universe expands forever. But what we observe is none of those. It's this top line. It's this case where the universe appears to have this extra thing, this extra energy inherent to space itself. So what does that mean if the universe has this extra energy? It means instead of a universe that expands and recollapses, or that expands forever, or that is on the border between expansion forever and recollapse, we have this other universe instead. We have one that accelerates. We have one that if we look at a distant galaxy that's a certain distance away, we see that galaxy expand from us. And the farther away the galaxy gets, the faster it appears to expand from us. The faster and faster it moves away. That's the thing that's accelerating. Not the expansion rate. I told you the expansion rate stays constant. What happens instead, what accelerates, is the speed of the individual galaxy. Now this is messed up, because what this means is that here's my galaxy now, right? It's pretty close by, and it's expanding away at a certain rate. But at a later time, that galaxy is going to be farther away from me. And there's more space in between us that's expanding. So the galaxy is going to move away faster. And this one's going to move away even faster, and the most distant one's going to move away fastest of all. I'm going to step on you for a while. So what this means is the more that we let time go on, I know, you better bark at them because they're leaving. Every galaxy that isn't already gravitationally bound to us, which is only our local group, it's us, Andromeda, and those loser galaxies that are super close by, that's what we get. Everything else, they might be bound in their own groups or their own clusters, but they're gone. Unless we go and get them, they're accelerating away, and the more time goes on, the faster they're going to move away from us. In fact, we don't really talk about how bad this is very often because it's a little depressing, but I love depressing. So if you were to say, I'm going to draw a circle around all the galaxies within those 46 billion light years that I could reach, if I went at the speed of light today, you'd only be able to get to 3% of them. 97% of all the galaxies in the universe that we can see are already unreachable, even if we left today at the speed of light. And every second that goes by, another 20,000 stars we lose the ability to ever reach. So start on that space travel program now. So yeah, that's it. Our little local group is like these few galaxies like right in here. That's our little local group, us and Andromeda, the Large Magellanic Cloud, the Small Magellanic Cloud, the Triangular Galaxy, and about 50 to 60 other dwarf galaxies. Everything else, the big Virgo cluster, that's a collection of over 1,000 Milky Way-sized galaxies. They'll all stay bound together, but we'll never fall in there. The Virgo cluster is expanding away from us at over 1,000 kilometers a second already. And as time goes on, that speed's only going to get faster and faster, thanks to dark energy. Our local group will at least stick around. Once you beat the expansion of the universe, once you overcome dark energy, once you're gravitationally bound, things are going to stick around. So you're in luck. Dark energy isn't going to come for you. Right? We'll get all the galaxies in us, all the stars in Andromeda, all these little satellite galaxies. We're all going to merge together. It's going to be awesome. Here's what's going to happen 4 to 7 billion years in the future. Right? 4 to 7 billion years in the future, the Milky Way and Andromeda are going to merge together. As they start to gravitationally interact, you'll start to see big spiral arms get stripped away. Right? You'll see stars get flung off into intergalactic space. Probably not us. You're going to get to see a huge burst of new star formation. One of the places the missing baryons are, and Sarah knows this, even if she hasn't found them yet, is they are in the interstellar medium. They are in the form of gas and dust and plasma in the halo of our galaxy. When galaxies collide, these gases will form new generations of stars. So we can expect a whole wild burst of new star formation when this happens. But once that merger is complete, we're going to become a giant elliptical galaxy that's a merger of the Milky Way and Andromeda. And we have already named it. It sounds like a terrible candy bar. Milkdromeda. What about in our solar system? What's our future? Right? Well, we'll stick around. I'm going to bet that we don't get kicked out of the galaxy during the merger. Less than 1% of stars will, so I'd bet on us. Unfortunately, in about 1 to 2 billion years, only 1 to 2 billion years, the Earth will look like this. Why? Because as stars like our sun go through their life, they heat up. Our sun right now is about 20% hotter and more luminous than it was when it was born a little over 4 billion years ago. In 1 to 2 billion years, it will heat up by enough that it should boil our oceans. It's a slow process. You cannot blame global warming on this. But if you come back 1 or 2 billion years from now and you see this, you can totally blame global warming on this. It's just a different type. So that's the future of life on Earth. 1 to 2 billion years is still a pretty good amount of time, so don't worry yet. The sun has maybe another 5 to 7 billion years before it becomes a red giant, blows off its outer layers into a planetary nebula, and contracts down to a white dwarf. Okay, good news for us. Mercury's going to get eaten by the sun when it becomes a red giant. Venus is going to get eaten by a sun when it becomes a red giant. Suckers, we're going to be just fine. The sun is going to undergo some mass ejection events, and that's going to gently blow Earth to a higher orbit. We're not going to get engulfed. So when the sun becomes, when it's done charring the solar system and charring the Earth, we'll still be a rock going around the sun. It's pretty good stuff. Our sun will contract down to a white dwarf, which will continue to be visible if there were any people left on Earth, which will not look like this in the future. The sun is going to stay as a luminous white dwarf for about a quadrillion years, about 10 to the 15 years before it goes dark. That is about 100,000 times the current age of the universe. There is not a single white dwarf star that has gone dark yet in the entire universe and won't be for trillions and trillions of years. The galaxy is going to look awesome if you could watch it from the Earth during that time, which you can't because we're going to be destroyed by the sun because of that whole boiling oceans thing. So let's pretend that this is from terraformed Mars. All right. So you're going to see, this is Andromeda, this is the Milky Way, you're going to see this big burst of star formation. That is fun, by the way. When you look up at a galaxy, have you ever seen pictures of galaxies with like these little pink things tracing their spiral arms? Have you ever seen that pink thing? Next time you see a big famous astronomy picture, look for those little pink lines around the spiral arms. That pink is real. When you form new stars, it emits light of a very particular wavelength. That is 656 nanometers, which is red to our eyes. You combine red and white light, and that's the pink you see. So keep a lookout for that in the sky 4 billion years from now. What about the stars, right? I told you about when our star is going to go dark, right? We can have these big, massive sun-like stars. When they run out of fuel, they turn into white dwarfs. When white dwarfs run out of energy after they radiated away for enough time, they go dark. What's the universe going to look like when our white dwarf goes dark? Well, our night sky is mostly stars in our own galaxy. And if we were to say, hey, I wonder what this is going to look like 10 to the 15 years from now, most of the stars will have burned out. All the ones that exist today will have burned out, but you form new ones. You just don't form as many in the future as you're forming now. That's something that we need to appreciate, is that when we look at the universe today, most of the stars formed 10 billion years ago already. As time goes on, we're forming new ones, but we're forming them at lower and lower and lower rates. So by time we get to when our star has burned out, the universe is going to kind of look like this. It's going to be really dark, and the only points of light that are left will be super red in color. They will be low in energy, low in temperature. Hopefully we'll have better eyes by then. And what about the future of black holes? You might say, this does not look like a black hole. And it doesn't, because there's no black hole that's done that yet today either. But in the far distant future, when the last star has burned out, when there's no more gas or fuel to form them, we will still have black holes. And they will still be black for a really long time. If you were to take the sun and say, I'm going to turn the sun into a black hole, it would stick around as a black hole for 10 to the 67 years. So one with 67 zeros after it. And then it would slowly start to lose its energy. Black holes evaporate due to a process known as Hawking radiation. And in the last few seconds of evaporation, that's when a black hole would emit the most amount of energy, so much that it would be visible to human eyes as a giant flash of light. The amount of energy that gets released in the last second of a black hole's evaporation is 500,000 times as powerful as the biggest atomic bomb we've ever detonated on Earth. In 1 second. Keep an eye out for that black hole. The most massive black hole in the universe that we know of will evaporate in 10 to the 100 years. And at that point, there will be no stars. All the other galaxies we see will have been pushed away due to dark energy, and the last black hole will have evaporated too. So, all of this is contingent on the story I told you being correct. All of this is contingent on the fact that we think dark energy really is energy inherent to space itself. You have also maybe heard this as a cosmological constant. You have also maybe heard this as vacuum energy. It is as though we took that same problem we started with and said, oh, here's what our universe is doing today. We looked back from now till the Big Bang, and we can extrapolate into the future and say the universe is accelerating and will expand at this rate. But that all assumes dark energy is that energy inherent to space itself. There are a number of different things it could be, though, and that's one of the things we're trying to pin down better. That's one of the goals of HETDEX. HETDEX is going to do an okay job, but if we really want to know, pin it down below 10%, below 1%, below 0.1% accuracy, we need bigger and better telescopes on the ground and in space to do these big surveys. Because it could be the case that this energy inherent to space itself gets stronger over time. What would that look like if things didn't just accelerate the farther away they got, but if that rate of acceleration went up and up and up? What would happen? Well, it means that galaxies that are bound together wouldn't necessarily stay bound together forever. As time went on and dark energy gets stronger, galaxies that look like they were going to be bound together can suddenly be pushed back apart again. Individual spiral galaxies spinning around would see the outermost stars get flung off, and then the inner ones get flung off too. Individual solar systems, if dark energy got so strong, we would see the Kuiper Belt disappear, and then Neptune and Uranus and Saturn eventually down to Earth. Even the planet itself would see its atoms get torn apart. And in the very final moments, everything, even the atoms that made you up, even the nuclei that made you up, would be ripped apart as well. That fate is known as the Big Rip. And it's possible. I don't think it's right, but you can't be sure unless you measure it and you find out, no, the universe is really doing that. Dark energy could also do the opposite thing. It could get weaker, or it could reverse in sign. So instead of getting stronger and stronger and accelerating way faster and faster forever, it could go the other direction. It could say, you know, we are going to reach a maximum size after all, and it is going to turn around, and it is going to recollapse, and we are going to end in a big crunch. And that's something we can also measure, right? So these alternatives, right, Sarah and I stole the same graphics. You start at the Big Bang, the universe appears to decelerate, it appears to be this Goldilocks case, and then dark energy takes over when the matter density dilutes enough, and you see things accelerate and expand faster and faster. But we haven't constrained it well enough to know that it won't rip, or that it won't turn around and crunch again. The way we're going to find out is through bigger and better telescopes and observatories. So how will we know? Well, the ESA is going to send up a mission called Euclid, and that is going to measure dark energy to better precision than anything we've done before. After that, NASA is going to send up the WFIRST mission, which is going to do even better. And around the same time as that, the LSST, the Large Synoptic Survey Telescope, is going to come online. So if you think that this stuff is fun, I'm telling you, it's going to get even better in the 2020s. All right. Now, I'm sure that there are no questions for me because I didn't have questions for you. That's not true. But with that said, let's stop here and see what questions you have. I'll answer the first one preemptively. Yes, this is a flask. Okay, we're going to do the same thing as last time. I'm going to look at hands, and I'm going to call on you, and then we're going to repeat your question. So you, sir, had a question.
Okay, so because the universe appears to be just a giant spider web, does cosmology anticipate the spider web expanding, or because of the closer clusters just forming dots, basically dots and clusters of universe galaxies that are just expanding out over time?
Okay, so this is a question about the cosmic spider web. So thank you for making me go all the way back to slide number 3. We're going to do it. Let's see how fast it is. The question is, I said the universe is like this cosmic spider web. So what does that mean when we're talking about what's happening to galaxies in the future? Is that a good paraphrase? Okay. So where we have this cosmic spider web, this is something that's formed over time. If I were to say, what did the universe start off as, right, and I didn't worry about the expansion, this would be an almost uniform. And over time, it would start to look like a sponge, where it had some holes in it, and it had some denser regions, but it was still pretty uniform. And as time goes on, the web gets more pronounced. You start to get matter really clustered together in these nexuses, and you get galaxies dotting along these filaments. And in the great regions in between, you have nothing. Then, after about 7 billion years or so, dark energy turns on. Dark energy becomes important. Matter has diluted so much that this energy inherent to space itself is more important for expansion. And at that point, anything that hasn't already become gravitationally bound never will be. So there's a limit to how big these clusters are already grown. And we already hit that limit about 6 billion years ago. So there are these gravitationally bound objects. They are going to stick around, but by and large, they're not growing still. They're not continuing to get larger and larger. Instead, each individual bound group of things that formed is expanding away from one another. All right. Other questions? Over here. Okay, there's this question about accelerating and decelerating. The question is, if dark energy is so powerful and the initial expansion is so powerful and we're accelerating today, why was the universe decelerating for so long? And the answer is, in this graph right here, that I'm going to get to if I can find it. This one. Okay. Imagine what happens early on over here, right? You have this tiny universe, and it's full of all this stuff. It's expanding fast. It's full of matter. It's full of radiation. It's full of dark energy. It's full of energy inherent to space itself. At the earliest times, who's most important? Think about what it is today, that we've got all these things in the universe, and now run your universe backwards. In the past, the energy density here for dark energy, it didn't go up when you went back into the past. It stayed the same. So the effect of dark energy today might make your universe expand at a certain rate. And early times, it made that universe expand at that same rate. It's slow. It's not accelerating fast today. It's just the universe is really big and there isn't a whole lot else going on. The matter, on the other hand, was denser and denser and denser and denser and denser. When the universe was 1/10 its size, the matter density was 1,000 times as important. When the universe was 1/1,000,000th its size, matter density was 10 to the 18 times as important. So the expansion rate due to matter was way more important in the past. Which means as the universe expands, it cools and the expansion rate slows down if matter was ever more important than dark energy. And even earlier on, radiation was even more important than matter. That's for about the first 9,000 years of the universe or so. Radiation was the most important thing. So the universe's expansion rate drops at a fast level due to radiation. And then finally radiation is less important than matter, and matter's like, oh thank God, we don't have to expand so fast. And the expansion rate goes down at a slower rate. And then matter density drops finally below the dark energy density, and dark energy says, oh thank God, now I don't have to decelerate anymore, and now the expansion rate can accelerate. So that's why the reason the universe was decelerating in the past is because matter and radiation were more important than dark energy was early on. All right, what other questions do we have? We have one right here in the front. I'm going to ask you to repeat that. Okay, when you talk about the first 9,000 years of the universe, what does that mean in the context of relativity? Astronomers have a lot of different ways of measuring time, right? So when I say the first 9,000 years of the universe, I mean, if I look back at the universe to the moment of the Big Bang, when the universe is first full of matter and radiation, and I understand it as it is today, that is 13.8 billion years of the past, and that's what I call time zero. So I count forward from that time where I can first describe the universe from the Big Bang. And I say, well, what are the things that happened, right? It's full of matter, full of radiation, full of everything, super energetic. I am doing all sorts of crazy stuff. Things are flying around, super energetic, smacking into one another. I'm making matter-antimatter pairs out of pure energy, and they're annihilating away into pure energy. And all of this is going on. And as I step forward in time and the universe expands, the radiation density drops and the universe cools. So after about 1 second, I'm not making matter and antimatter anymore. And after about 3 minutes, it's cool that I can make atomic nuclei instead of just having protons and neutrons. And after 380,000 years, I can form neutral atoms for the first time, and I don't have to smash it apart immediately anytime I put a proton and an electron together. 9,000 years is counting forward from that. That's the moment where radiation has finally diluted enough that its wavelength has stretched so much that in terms of what makes a bigger contribution to the total amount of energy in the universe, matter for the first time has passed radiation. Let's see if there are others, and if there aren't, then we can come back. Yeah, you have a question.
Yeah, what are your thoughts on multiverse? Just if you have an opinion on that.
Okay, this is an open-ended question on what are my thoughts on the multiverse. And do I have an opinion on that? I do have an opinion on that. That's the easy question. What is my opinion on the multiverse? So, the Big Bang, I've talked about that as being the moment we can first describe the universe as being expanding and full of matter and radiation. There is a theory that is generally accepted, known as cosmic inflation, that came before the hot Big Bang and set it up. It says that at some very, very high energy, not like the tiny bit of energy inherent to space today, but at some early times, there is some huge amount of energy inherent to space itself, and that space expanded at this hugely accelerating rate. And in some pockets of that universe, due to quantum fluctuations, inflation ended. That energy from space itself got converted into matter and radiation in some place, including here. The multiverse is a prediction you get out of inflation that says, look, in lots of places, you don't have the right quantum fluctuation and inflation continues and you keep making more and more space. But the more space you make, the more chances you have for the right quantum fluctuation to occur, for inflation to end, and for a Big Bang to start. So what cosmic inflation tells you is that we expect there to be other regions of space that are not connected to what we call the universe, that are separated by these regions of inflating space where these regions have their own Big Bang. They have their own place where inflation ended, where the universe began with matter and radiation, and we are not connected to them. Now, I do not know, and I don't think anyone professes to know, how many of these other universes there are. Are there an infinite number? Only if inflation has been going on for an infinite amount of time. Has inflation been going on for an infinite number of time? We believe our universe has information about the final 10 to the minus 33 seconds of inflation in it. That is not a big number. So it's possible that there are an infinite number of universes like this, but if these theories that we have that appear to describe our universe are valid, then there should be other regions that aren't contained in our own that have had big bangs, that have the expanding universe, that maybe have different laws of physics from what we have, and we don't know. Shameless plug, you should read chapter 8 in my book, where we talk about this at length. We have time for one more question, and we are going to go with the lady in the front row. The question is, how do I feel about Fermi's paradox, given that I invoked life and brought this question on myself? Fermi's paradox, for those of you who don't know, say, if the conditions for life are everywhere, and we have all these different chances, all these stars, all these galaxies, all these planets, all these ingredients, then where is everybody? Where are all the aliens? And why haven't we heard from them yet? That is Fermi's paradox. And the simple, non-committal answer is because somewhere there is a hard step. It's not easy to go from, oh, we were just matter and radiation, to we are intelligent, spacefaring human beings. We're not even really spacefaring yet. Like, we're struggling at this. But there is some step that's hard there. Now, we know some of the steps that aren't hard. We know it's not hard to make atoms. It's not hard to make stars. It's not hard to make galaxies. It's not hard to make heavy elements. It's not hard to make planets. It's not hard to make rocky planets at the right distance from their star for liquid water to be on them, with the right ingredients for life on them, with organic materials from interstellar space populating them. That part is not hard. But is it hard to take that step to go from organic materials to life? Is it hard to take that step that goes from life to complex multicellular information-containing life? Is it hard to take that step from, say, the Cambrian explosion to intelligent tool-using, spacefaring, radio-using, human being-type people? My guess is one or more of those 3 steps is a lot harder than some schmo in the 1940s saying, boy, I wonder where everybody is. I have been told that this talk is over. Thank you.
So if you didn't have your burning questions answered, Ethan's book is for sale, and likely the answers are in that book, so you come see him afterwards. So I just want to say thanks again to both of our speakers, Sarah and Ethan. Thanks to Peddler again for hosting us. Don't forget to tip your lovely bartenders for serving you all night. Let's give them a round of applause. Thanks to you all for coming out. As usual, I'll be back again next month on June 28th, so we hope to see you all again for warm weather, finally. Thanks.